In this video, we will look at the area and perimeter of a triangle. We will start by looking at the simple formulas for perimeter and area. Then we will look at the area formula in a bit more detail to see why it works. We will finish by looking at some special cases: obtuse triangles, triangles where we know the two sides are an included angle, and triangles where we know three sides, and finally equilateral triangles. First, let's look at the perimeter of a triangle. Here is a triangle with sides of length A, B and C. The perimeter is the distance all the way around the shape. This includes the length of side A, the length of side B and the length of side C. So the formula for the perimeter of a triangle is A plus B plus C. This simple formula assumes that we have been given the lengths of all three sides. If we don't have this information, we will need to use other methods to find the sides. For example, we might need to use the sine or cosine rule. To find the area of a triangle, we need to know two things: the base and the height of the triangle. The base is one side of the triangle. We can use any side, but in this case we will use the side AB. We will assume that the triangle is drawn so that the base is horizontal and at the bottom of the triangle. The height is the distance from the highest point of the triangle to the base. In this case the highest point is the vertex C, which is opposite the side AB. We must draw a line that is at a right angle to AB. We call this a perpendicular distance. The area of the triangle is half the base times the height. Why does this formula give us the area of the triangle? The easiest way to understand it is to look at a right-angled triangle. In a right-angled triangle, the base is the side AB and the height is the side AC. Now let's draw an identical triangle that shares the same diagonal side as the original triangle. These two triangles form a rectangle. We can find the area of the rectangle by multiplying the width and the height. In this case, the width is the base, so the area is the base times height. Since the rectangle is made up of two identical triangles, we can see that the area of one triangle is half of the base times the height. The previous technique applies to right-angled triangles. How can we find the area of a non-right-angled triangle? Well, we can apply the same technique of creating a second identical triangle. This time, instead of creating a rectangle, the two triangles create a parallelogram. We can perform an extra step to convert this shape into a rectangle. We cut off the triangular section at the left-hand side of the parallelogram and slide it across to the right-hand side. This gives us a rectangle. The height of the rectangle is equal to the height of the original triangle. The width is equal to the base of the triangle, so the area of the parallelogram is equal to the width times the height. And since the parallelogram is made up of two identical triangles, the area of each triangle is half the base times the height. Obtuse triangles can sometimes cause confusion. The point C is outside the base of the triangle, so to find the height we need to extend the baseline to the left. Even though we have extended the baseline, we must still use the line AB as the baseline for our calculation. Here's what happens when we add the second triangle. We get a parallelogram just like before. It is just slanted to the left instead of the right. The calculation is still exactly the same. The area of the triangle is half the base times height. Sometimes we might not be given the base and height of the triangle. We might be given different information. In this case we know two sides and an included angle, that is an SAS triangle. How do we find the height of this triangle? The trick is to notice that the height line splits the triangle into two right-angled triangles. We will look at the triangle on the left side. We know the angle A and the length B, which is the hypotenuse of the triangle. We are trying to find the side opposite to the angle A. We can use the sine function to find this. Sine A is equal to the opposite over the hypotenuse, which in this case is the height over B. Rearranging this gives us height as B times sine A. Returning to the main triangle, the base of the triangle is length C. We now know the height is B sine A, so the area, half base times height, is equal to half C times B sine A. We usually write this as half BC sine A because it somehow sounds more natural. What if we know the three sides of a triangle? One thing we could do is use the cosine rule. The cosine rule allows us to find an angle given three sides. If we know an angle and three sides, we can apply the SAS rule from before. There is nothing wrong with this method, but there is an easier way using Heron's formula. To use this formula, we must first calculate the value of A plus B plus C, all divided by 2. This is half the perimeter of the triangle. We will call this value S. The area is then given by this long but fairly simple equation. We will finish by taking a look at equilateral triangles. In an equilateral triangle, all sides are equal and all the angles are equal. Since we know that the angles in a triangle always add up to 180 degrees, this means that each angle in an equilateral triangle must be 60 degrees, since 3 times 60 is 180. In fact, if we know the length A of each side of an equilateral triangle, we know everything about the triangle. So you'd expect the perimeter and area to have formulas that only depend on A. The perimeter is usually given by the lengths of the three sides, A plus B plus C. But since all three sides have length A, the perimeter is 3 times A. What about the area of an equilateral triangle? We will start with the SAS formula. Area is half BC sine A. Sides B and C are both equal to side A. Angle A is 60 degrees. The sine of 60 degrees is exactly half the square root of 3. So the area of an equilateral triangle is half times A times root 3 over 2. This simplifies to root 3 over 4 times A squared. If you enjoyed this video, please like and subscribe. You can find more resources at graphicmaths.com. The link is in the description below.